I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 12, Low-Side Lobe Phased Array Antenna Measurements Using Near-Field Scanning. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's a course content breakdown by topic. This is lecture 12. We'll be covering phased array theory, antenna measurement techniques. We'll be taking into account array mutual coupling, and far field and near field characteristics. Chapter 12 of the book Adaptive Antennas and Phased Arrays for Radar and Communications has additional information to supplement this lecture. So the purpose of this lecture is to review the planar near field scanning technique to quantify low side lobe phased array antenna radiation pattern performance. In the previous lecture, we used this technique to measure the performance of a displaced phase center antenna. Here's an outline of the talk. After a brief introduction and background, I'll describe the methods and materials, some results, and then summarize. And so by way of introduction, adaptive phased array antenna systems have been explored extensively by numerous researchers since the 1950s. And the primary functions of a phased array antenna are to provide rapid beam steering, in some cases multiple phase centers, and in many cases low side lobes. And so in this lecture we're going to concentrate on measuring the performance of a low side lobe phased array. This slide shows a phased array antenna aperture and a near field scanning test plane. So the near field is typically measured on a grid of points close to the antenna under test. So there's a single near field probe and it's moved to many points covering a large test plane, larger than the aperture of the antenna. So typically in a phased array, there are a number of TR modules that are used to electronically steer a beam in a desired direction, and an amplitude taper used to provide low side lobes. So with the near field measurement technique, we will compute the far field pattern from the measured near field data. So let's describe the methods and materials. Now to mathematically transform the near field data to far field data, we need to know the tangential near zone electric field. So here's a low side lobe phased array antenna aperture. Here's the near field sampling plane. And we measure E tangential at a number of regularly spaced points on this test plane. Ideally, we'd like to do the measurements in a large anechoic chamber. So to summarize, a mathematical transformation can be used to obtain the far zone fields from the tangential components of the near field. And we'll show how to do that. And so in order to do the near field to far field transformation, we need to know the relationship between the electromagnetic fields and something referred to as the plane wave spectrum. So the electromagnetic fields are described by the electric and magnetic fields, E and H. So here we have a radiating aperture in the XYZ rectangular coordinate system, and the electric field E can be determined at points X, Y, and Z. R is the observation vector, and theta and phi are the spherical coordinate angles. And now to describe the plane wave spectrum, consider the propagation vector components kx, ky, and kz. So k is the propagation vector, and that's equal to kx x hat plus ky y hat plus kz z hat, where the hat refers to a unit vector. So for plane wave spectrum, it's a vector as a function of kx, ky, and kz. And we want to show how to obtain the plane wave spectrum from the electric field. And once we obtain the plane wave spectrum from the near fields, we're able to get the far fields, as we'll show. So to develop the field and plane wave spectrum relations, consider the vector wave equation, which can be derived from Maxwell's field equations. And the wave equation is shown here as del squared E plus k squared E equals 0, where E is the electric field and k is the wave number, as shown here. K is equal to magnitude of the vector wave number, where k is equal to the square root of kx squared plus ky squared plus kz squared. And so an elementary solution to the wave equation is shown here. E is equal to the plane wave spectrum multiplied by a phase factor. Now, continuing the development, as we said, the electric field can be written in terms of the plane wave spectrum times a phase factor involving the wave number components. So the wave number components are shown here in terms of the spherical coordinate angles. And what we can do is solve for k sub z, and we show that it depends on kx and ky as shown here. And this quantity has real and imaginary solutions. So kz is a real quantity when kx squared plus ky squared is less than k squared, and kz is purely imaginary when kx squared plus ky squared is greater than k squared. And so what we've done here is now write the electric field in the near field that's equal to the plane wave spectrum times this phase factor, which is written in terms of the kx and ky components. Kx and ky are real. So there are two wave types. There are reactive waves that don't propagate to the far field, and there are radiating waves that do propagate to the far field. And so if kx squared plus ky squared is less than k squared, this is known as the visible region, or the radiating region, and this produces uniform plane waves that propagate away from the array. In contrast, if kx squared plus ky squared is greater than k squared, then this is defined as the invisible region, or reactive region, where there are non-uniform plane waves or evanescent waves. And the dashed circle represents the boundary between the visible region, the radiating region, and the invisible region or reactive region of the antenna under test. So continuing the development, here we've written the plane wave spectrum in terms of the three rectangular components, x, y, and z. And if we substitute this into the solution of the wave equation, and if we use the Maxwell equation divergence of d equal to 0 in free space, we can solve for the z component of the plane wave spectrum, which is shown to be dependent on the x and y components of the plane wave spectrum. So a sub z is the z component of the plane wave spectrum, and it is the dependent variable. Now in this lecture we talk about two types of near-field transformations. We'll talk about a known near-zone electric field and a known near-zone probe received voltage. And we'll start out by looking at the known near-zone electric field. So a general solution to the wave equation is a linear combination of all physically admissible elementary solutions. And so what we're showing here is the near-zone electric field at the point xyz, and that's equal to the double infinite integral of the plane wave spectrum times the phase term dkx dky. Now suppose we have a known tangential near-zone electric field, E sub t, then we can compute the plane wave spectrum as the inverse Fourier transform. So the plane wave spectrum is equal to 1 over 4 pi squared, the double infinite integral of the tangential electric field, and we evaluate it at a constant z distance away from the antenna. So this is taken over the xy plane. So again, here we've written the plane wave spectrum in vector notation in terms of the tangential electric field. And specifically, if the tangential electric field consists of x and y components only, and that's over the sample plane, now we can write a sub x and a sub y in terms of kx and ky, and so we can express the x and y components of the plane wave spectrum as the finite integral over the xy plane of the x component of the electric field evaluated on a plane at z0, and the y component of the electric field also evaluated at z0. So the x and y components of the plane wave spectrum can be computed from finite integrals from either calculated or measured electric field data. And so the above finite integrals can be evaluated using the inverse fast Fourier transform algorithm. And so from the reference by Rhodes, the book, Synthesis of Planar Antenna Sources, in the far field of the antenna under test, the electric field can be written asymptotically in terms of the plane wave spectrum as shown here. The electric field in the far zone is proportional to cosine of theta, e to the minus jk r over r, where r is the range distance, times the plane wave spectrum. We just showed in the previous slide how to compute the plane wave spectrum from the near zone electric field. And now the far field components E theta and E phi can be obtained by converting from rectangular components AX, AY, AZ to spherical components. So to summarize, we take a near zone electric field, either calculated or measured, at a distance Z0 from the antenna under test. We compute the plane wave spectrum, A, as a function of Kx and Ky, and from that, using the above equation, we find the far zone electric field, E, as a function of r theta phi. Now we're going to discuss the case where we have a known near zone probe received voltage, because for an actual near field testing system, we would use a probe to receive a voltage where we would not directly know the near zone electric field. We have to compute that separately. So now we consider the case of a known near zone probe received voltage, which corresponds to the practical case of a near field scanning measurement system. Now let's consider the linearly polarized case for a test antenna with E theta polarization. So in this case, the radiation pattern of the near field probe affects the near field measurements. And so here we have a phased array antenna aperture, and here's the near field range. We're going to move the probe and sample the tangential electric field, or measure a voltage as a function of position of the probe. So the probe pattern E of theta phi distorts the measured tangential electric field, or the measured voltage, and we need to compensate for the probe to determine the correct far field pattern of the phased array antenna under test. So we either calculate the voltage or we measure the voltage. And so this slide talks to the subject of near field measurements and probe compensation. And the reference by Paris, Leach, and Joy, published in the IEEE Transactions on Antennas and Propagation, covers the theory in great detail. So in practice, the near field sampling probe provides a measured voltage rather than a measured electric field. So probe compensation is required to take into account the probe plane wave spectrum, little a. So what we do is we measure or calculate a probe voltage, we determine the probe distorted plane wave spectrum of the antenna, we perform probe compensation to determine the far zone electric field. So here we have the measured probe voltage Vx at a distance Z0 from the antenna under test, and that's equal to the double infinite integral of the plane wave spectrum of the antenna, which is desired, times the probe plane wave spectrum, and then there's a phase term, and we're integrating on Kx and Ky. And so the probe distorted plane wave spectrum of the antenna under test can be written as the product of the plane wave spectrum of the antenna that's desired times the probe plane wave spectrum. And note that the probe distorted plane wave spectrum can be written as a double infinite integral of the probe received voltage with a phase term. And so to back out the true plane wave spectrum of the antenna, what we need to know is the probe radiation pattern. And so what we need to do is determine the probe radiation pattern, either measure it or calculate it, and relate it to the plane wave spectrum of the probe, which is shown here. It's proportional to the cosine of theta and e to the minus jk r over r times the probe plane wave spectrum. And so the probe distorted plane wave spectrum can be written in terms of the dot product of the electric field of the antenna under test that's desired times the electric field of the probe antenna, and that's equal to cosine theta e to the jkz z0 times the probe distorted plane wave spectrum. And so for the simple case where we're only concerned with the E theta component, the E theta component can be written as the product of a constant times cosine of theta, e to the j k z z naught, times the ratio of the probe distorted plane wave spectrum divided by the electric field pattern of the near field probe. And so this expression here shows how to take into account the effects of probe distortion. And E theta is the true radiation pattern that's desired. So we've covered two different ways of converting from near field to far field data. Now let's talk about phased array modeling. In the example shown in this lecture, we're going to be doing near field modeling for a monopole phased array antenna. So this shows a monopole array over a ground plane. And lecture number 9 talked about a detailed theory for analyzing large arrays of monopole phased arrays. We assume a sinusoidal current on each of the monopoles. These monopoles are approximately a quarter wavelength long. And now to model a monopole array over a ground plane, we use an equivalent dipole array in free space for convenience. And for the case of sinusoidal currents, the near zone electric field can be readily determined. And we use the method of moments to analyze the array. We compute an impedance matrix as the open circuit mutual impedance matrix plus a load impedance matrix times the identity matrix. And this type of analysis was described in lecture 9. So in modeling the near field of a phased array, we use two approaches in this lecture. We use something that I refer to as the field point theory and the V-Dipole Probe theory. Now the field point theory simply calculates the tangential electric field at a point in front of the antenna under test. And so that can be readily done for any type of radiating element. In the case shown in this lecture, we use monopoles, but they could be dipoles, microstrip patches, waveguides, or other types of radiating elements. So each of the antenna elements has a coherent oscillator and a load impedance. And for the example shown here, the array is considered to be transmitting, and we're calculating the tangential electric field in front of the antenna. There's an open circuit mutual impedance term between each element, and we compute the electric field by the method of moments as shown here. We compute the currents in each of the antenna elements by inverting the impedance matrix and multiplying by the voltage excitation matrix. And we compute the electric field in front of the antenna by summing up the electric field due to each of the phased array antenna elements. Now in contrast, in the V-Dipole probe theory, which I'll be describing, we're computing the probe voltage by the method of moments, and the probe antenna is modeled as a V-dipole. We use a V-dipole in order to shape the radiation pattern to match an arbitrary practical near-field probe, such as a waveguide. So in this situation, the V-dipole is transmitting. We have a receive array. There's mutual coupling between the array receiving elements, and then there's a receiver connected to each of the elements, which has a load impedance, and we're computing the receive voltage at each of the elements in the array. The array beamformed output can be written in terms of the dot product of a weight vector times the receive voltage matrix. And this is done at each position for the near field probe at a constant distance z0 away from the array. So these are the two approaches, a field point theory where we get the electric field directly, and the V-dipole probe theory where we're computing the actual voltage received at the array. This slide shows the calculated radiation pattern for a V-dipole probe antenna. In the moment method analysis for near-field probing, we use a single piecewise sinusoidal current to approximate the current on the V-dipole. And that's shown to be valid by comparing the radiation pattern as the number of overlapping sinusoids is increased from 1 to 5. And so what we see is there's very little difference in the radiation pattern for the case where the V-dipole has a 45-degree angle. So the single piecewise sinusoidal current function is sufficient for this analysis. So let's now describe a low-side-lobe phased array prototype. A large monopole array with 32 radiating elements was fabricated. This array contained 2 rows of passively terminated elements surrounding the 32-element active array. This photograph shows a typical near-field scanner that can be used to sample the near field. This slide shows a block diagram for the receive portion of the transmit-receive TR module in the 32-element linear array. So here's the antenna element. After going through the low noise amplifier, phase shift is applied in this first mixer, and then the received signal is down converted, where a variable attenuator is used to apply the desired taper, and then the phase and amplitude weighted signal of each of the 32 elements goes to this 32-way power combiner. Let's now describe the near-field scanning system. A rectangular waveguide probe was used to scan the near field. The rectangular probe was surrounded by anechoic material, and we'll show that the anechoic material does have an effect on the radiation pattern of the rectangular waveguide. And this shows the scanner that was used to scan the near field of the 32-element linear array. This slide just shows that the measured VSWR for the rectangular waveguide probe is below 2.0. So the near field probe has a good VSWR over the 1.2 to 1.4 gigahertz test band. This slide shows the measured far field patterns for the waveguide probe antenna with and without microwave absorber. And what we see is that the microwave absorber has a significant effect on the probe pattern. The dashed curve is without absorber, and the solid curve is with absorber. This was measured at 1.3 gigahertz in the E-plane for this rectangular waveguide probe. And so the reason we used a V-dipole in the computer simulation was to vary the angle of the V-shaped element to match the radiation pattern of the rectangular waveguide probe with the absorber. So let's show some results. So this slide shows the V-dipole probe pattern as a function of the tilt angle of the V-dipole compared to the measured radiation pattern of the rectangular waveguide probe. So the solid curve is the measured radiation pattern of the rectangular waveguide probe with the absorber. And the case where the V-dipole tilt angle is 45 degrees matches pretty close to the radiation pattern of the rectangular probe. And so to summarize, there's good agreement between the measured waveguide probe pattern and the V-dipole probe pattern when the tilt angle is approximately 45 degrees. Now, in order to fully understand the plane wave spectrum that's calculated from the near zone electric field, it's useful to understand the grating lobe positions for a linear array. And now normally when an array is designed, the array is designed to avoid grating lobes. However, the grating lobes could exist in the invisible space where they're not propagating, and we can actually see or calculate the grating lobes using near field data. And when we do the mathematical transformation, we'll see the grating lobes in the plane wave spectrum. So here's the array factor for a linear array. It's just a summation of the weighted elements with a phase term. The array weights are equal to an amplitude coefficient times a phase term to scan the beam in the desired direction. And so if we substitute the array weights into the array factor, we get this expression shown here, from which we can calculate the grating lobe positions in terms of the wave numbers as shown here. K sub x for the mth grating lobe is equal to k times sine of the scan angle plus 2 pi over the array element spacing d sub x times m, where m is equal to plus or minus 1, plus or minus 2, etc. Now if k sub x is greater than 2 pi over lambda, this would refer to invisible space where the grating lobes are not propagating. Here's an example when the spacing is slightly less than a half wavelength and the scan angle is minus 30 degrees. We compute the grating lobe positions as shown here. And so since the magnitude of these grating lobe positions is greater than 2 pi, the grating lobes are in the invisible space. And we'll see these in the calculations that follow. Now this slide shows the grating lobe pattern for the array factor in visible space and in the invisible space. So it's a 32-element linear array of isotropic elements. Here's the main lobe with the beam steered to minus 30 degrees. And here's grating lobe number minus 1, grating lobe plus 1, and grating lobe plus 2. And these are located at the positions calculated from the prior slide. Notice in this example we chose a 40 dB Taylor taper. Now there's a spectral aliasing in the FFT process. So the largest wave number that's produced in the fast Fourier transform process is given by Kx max is equal to pi over dx, where dx is the sample data spacing in wavelengths. This diagram shows the array with array element spacing capital Dx and the sample plane with spacing little d sub x. If we assume an nx point FFT including zero filling and let capital K sub x be the unfolded FFT transform index, then the transform wave number is given by the expression shown here, and any large plane wave spectrum components above the maximum wave number, Kx max equal pi over dx, will have an alias in the spectrum. And any large plane wave spectrum components above the maximum wave number will have an alias in the plane wave spectrum. So this slide shows an example monopole array and a near-field centerline scan, which is used to collect the near-field data. And so this is a 32-element linear array of approximately quarter wavelength monopoles with a 40 dB low-side lobe Taylor taper. There are 2 rows of passively terminated monopole elements. We're doing the simulations for an array with an infinite ground plane, and the measurements are for an array with a finite ground plane. We calculate or measure the electric field at a distance z0 in front of the antenna under test. So we'll start by showing the calculated near-field distributions for the low-side lobe monopole phased array. Here we're comparing the field point theory, where we calculate the electric field directly, and we compare it to the V-Dipole Probe theory, where we're calculating a voltage. So on the left is the calculated amplitude versus the probe position, and we see very good agreement in the amplitude. These data are taken at a distance of 0.55 lambda from the antenna. On the right we show the phase. We see the linear phase slope because we're steering the main beam away from broadside. And there's very good agreement between the 2 methods of near-field calculation. This slide shows the calculated plane wave spectrum from the calculated near-field data from both the field point theory and the V-Dipole Probe theory. And so what we see in the plane wave spectrum in the visible space, we have a main beam, and so we see the low side lobes. And here we have in the invisible space the first grating lobe, which is seen by both the field point theory and the V-Dipole Probe theory. And we see the grating lobe minus 1. And now the second grating lobe, which would normally be over in this region, is aliased into the negative wave numbers. And here we see an alias of grating lobe number 2 in the field point theory. Now we can calculate the far field patterns from the calculated plane wave spectrum. Here we're comparing the field point theory to the V-Dipole Probe theory. We see excellent agreement between the 2 theories. Here's the main beam steered to minus 30 degrees, and over the visible space, plus or minus 90 degrees, we see the low side lobe radiation patterns. We also see the deep null because of the monopole radiating elements. So in summary, we have good agreement between the 2 methods of far field calculation using the near field data. This slide shows the calculated far field patterns using the near field transformation and a direct far field calculation. So the solid curve is a direct far field computation, and the dashed curve is the near field to far field transformation using the field point theory, using the direct near field electric field and transforming it to the far field. We see excellent agreement between the two methods of calculation for the far field, by either the direct method or the near field to far field transformation. Now this slide shows the measured and calculated near zone received voltage for the phased array antenna. Here we're comparing the V-Dipole probe theory to measurements for the 32 element test bed. So on the left is the amplitude calculated and measured, and there's very good agreement. And we see good agreement between the measurements and simulations for the phase as well. And again, the phase slope is due to the main beam being steered from broadside. This slide shows the measured and calculated near zone received voltage for the phased array antenna, where we're comparing the V-Dipole probe theory to the measurements. We're just looking at the amplitude. So on the left, we're showing the full scan, and on the right, we're showing an expanded view of this region in here. And what we see is there's some ripple, and each of these ripples corresponds to one element of the array. You can actually see the element spacing. And the measured ripple is higher than the simulated ripple, but the amount of ripple is similar. It's a half a dB for the measurements and 0.2 dB in the simulations. So in summary, there's good agreement between the measured and calculated near field, and the peak-to-peak ripple difference is about 0.3 dB. This slide shows the measured and calculated plane wave spectrum for the monopole phased array. Here we're comparing the V-Dipole probe theory to the measurements. And what we see is in the visible space, we see the main beam and the low side lobes. We can see the first grating lobe in imaginary space in both the measurements and in the simulations. And we also see the left grating lobe as shown here. So we can summarize and say there's good agreement between measurement and simulation in the visible space and in the invisible space regions. And finally, we show the measured and calculated far field pattern for the monopole phased array. This is the V-Dipole probe theory compared to the measurements. And so we're plotting the data from -60 to +60 degrees for theta. We see the main beam formed at -30 degrees. We see the low side lobe radiation pattern. The side lobes are below about 40 dB. On average, the measured side lobes are -46.7 dB, and the average side lobes in the simulation are -48.6 dB. So they're in very good agreement. So let's summarize. In this lecture, the theory of near-field scanning for measuring the performance of low-side-lobe phased array antennas has been reviewed, and examples of measured and simulated low-side-lobe array near-field and far-field characteristics have been given. Chapter 12 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, can be used to supplement the material presented in this lecture.